Today we're going to take a look at a new technique called integration by parts. Now, integration by parts is an incredibly important technique because it essentially undoes the product rule. So whenever you have integrals that involve a product of two functions, integration by parts is a natural first place to go to see if you can use it to solve the integral. For example, we can already solve integrals that are complex, such as cosine of x e to the sine of x, or 2x, or perhaps 1 over x ln of x squared dx, or secant squared of x tangent x dx, and so forth. So each of these integrals involves just a simple u substitution, because we have some main function and the inside function has a derivative that's sitting right here in the integrand. So the derivative of sine is cosine, and so forth. So each of these sorts of integrals we can use just substitution for. However, if we encounter an integral like x e to the x, well, this seems like a very simple function. It seems like something we would want to be able to know an antiderivative of. We're kind of stuck right now. We can't use substitution because this x outside is not the derivative of the inside function. We can use substitution on x e to the x squared, but it fails on x e to the x by itself. So for an integral like this, we turn to a technique called integration by parts. The formula is the following. So the integral of u dv is equal to uv minus the integral of v du. So this is the main formula that you should know. Integral u dv equals uv minus the integral of v du. And we'll see how this works when we discuss the examples. But right now, what we have is u and v are both functions of x. So u is a function of x, v is a function of x, and then du represents u prime of x dx. So du is just the differential of the function u, and then dv represents v prime of x dx. So when you start off with an integral like x e to the x dx, the dx is going to belong to the dv that you have in the formula. So then we just need to identify v prime of x and then proceed by applying this formula. So here we have the function u times the function v minus the integral of the function v times the differential of u. So before we explain where this formula comes from, I'd like to point something out with this. Essentially what this is, it's kind of like like some sort of pulley system, like an elevator. So we have two functions u and v, or u and dv, that are initially in our integral. So u is here, and then dv is right there. So we replace this with u times v, and then on the right-hand side we end up with a second integral. So instead of having an integral of u dv, we end up with an integral of v du. So here's my function u, here's dv. So instead of having u, I'm replacing u with du. So u is differentiated and it's moving down. And dv is replaced with v. So dv is being integrated, it's being moved up. So basically you have u times dv, and you're replacing it with du times v. So basically when we have a product of two functions, when we apply integration by parts, one of these functions is differentiated and the other one is integrated. So in this example, we would want to differentiate x so we can identify x with the function u, and then we'd like to integrate e to the x. And the reason to do this is for our u, we always set u to equal something that will eventually differentiate to 0, because instead of having an x, we'll be left with a constant. Instead of an x squared, we would be left with an x, because the u is being replaced by its derivative. So u typically goes toward simplicity as we differentiate it. So if we set this up just to see how this works, u would be set equal to x, dv we would set equal to e to the x dx. Now from this we can differentiate u, and we obtain du is equal to dx. And then we would integrate dv, and we obtain v is equal to e to the x, right? Because if v is equal to e to the x, then dv would equal e to the x dx. So according to this formula, this integral, so the integral of x e to the x dx, should equal u times v. So x, that's my u, and then v is right here. So u times v, x e to the x, minus the integral of v times du. So those are these two. So minus the integral of e to the x dx, like that. So this was u, this is dv, and it's equal to u times v minus the integral of v, and then du is just dx. So that's how you would apply the formula for something like this. Now the integral of e to the x dx we can solve because we know the integral of e to the x, it's just e to the x. So we get x e to the x minus e to the x, and of course plus c. So the integral of x e to the x is given by x e to the x minus e to the x plus c. Now we can check this by differentiating the right-hand side. So let's differentiate the right-hand side and check to see if we get the right thing. So if we start off with x e to the x minus e to the x, when we take the derivative, we have to use the product rule on this first term. So it becomes x times the derivative of e to the x, which is just e to the x, and then plus e to the x times the derivative of x, which is 1. So we get x e to the x plus e to the x, and then the second term we get minus the derivative of e to the x is e to the x. So this simplifies to x e to the x. So this is indeed the antiderivative of x e to the x. So we just showed that x e to the x, so the integral of x e to the x, is equal to x e to the x minus e to the x plus c. So you can see it, it's a fairly powerful technique. You just need to get used to this notation of the u, the v, the du, and the dv, and then you can apply integration by parts to a variety of situations. So next I want to show where integration by parts comes from. So where does this formula come from? So the formula again was integral of u dv is equal to uv minus the integral of v du. I mentioned earlier that what integration by parts does is it essentially undoes the product rule. So before we understand integration by parts, let's go back and review the product rule. Now, if we have a product of two functions, like say y is equal to f of x times g of x, when we differentiate this, we get dy dx is equal to f of x, g prime of x, plus f prime of x, g of x. Right? First times the derivative of the second, plus the second times the derivative of the first. So that's what happens when we use the product rule. So I'm going to re-express this in a slightly different way. Instead of using f and g as my functions, I'm going to use u and v. So I'm going to say, what happens when we take the derivative of u times v? And I won't bother saying u of x and v of x, it will just be u and v. And instead of taking the derivative, I'm just going to take the differential. So recall that when we take the differential of y, it's shorthand for dy dx times dx. So it's essentially the product rule, except I'm multiplying everything through by the dx. So the differential of uv would be u times the differential of v plus v times the differential of u. So to see where this comes from, this is essentially, if we take the derivative instead of the differential, we can write it like this. Right, so the derivative of u times v is equal to u times the derivative of v plus v times the derivative of u. Now if we multiply everything through by dx, we get this equation right here. So the du literally represents du dx times dx. The dv literally represents dv dx dx. And the duv represents duv dx dx. So this equation is exactly the product rule expressed using differentials instead of derivatives. So what we do next is we solve this for u dv. So I'm going to set u dv equal to the differential of uv minus v times the differential of u. Okay, so from this, all we need to do is integrate. So if we integrate this, we get the integral of u dv is equal to the integral of the differential of uv and then minus the integral of v du. Now the integral of the differential is just going to equal u times v. So integral of u dv equals uv minus the integral of v du. So you see this is exactly undoing the product rule. And the other way to think about this is if you differentiate this expression up here into the integration by parts formula, to differentiate u times v, you would get u times the derivative of v plus v times the derivative of u. So this works exactly correct. So this is basically an integral form of the product rule, and that's where the formula comes from.